Without further ado, we'll introduce our moderator for today, Kenavis Smith. Kenavis is the manager of the Professional Masters in Engineering program at Texas Engineering Executive Education, which is the continuing and professional education provider of the Cockrell School of Engineering at UT Austin. Take it away, Kenavis.
Thank you so much, Javier. And as Javier mentioned, my name is Kenavis Smith, and I have the distinct pleasure of introducing our esteemed speaker, Dr. Moriba Jah. Dr. Jah is an American space scientist and aerospace engineer known for his contributions to orbit determination and prediction, especially as related to space situational awareness and space traffic monitoring. Moriba Jah is an associate professor of aerospace engineering and engineering mechanics at the University of Texas at Austin, where he is the holder of the Mrs. Pearlie Deshelle Henderson Centennial Fellowship in Engineering, and he is the director of the Computational Astronautical Sciences and Technologies, which is a group within the Odin Institute of Computational Engineering and Sciences, as well as the lead for the Space Security and Safety Program at the Robert Strauss Center for International Security and Law. His research interests include the non-gravitational astrodynamics and object tracking, prediction, information fusion, space object detection, and spacecraft navigation. And on top of that, he holds a PhD from the University of Colorado. So without further ado, please help me welcome Professor Moriba Jah.
Look, thank you so much. Pleasure to be here with you folks, and happy and honored to kick off this new season, as it were, of TexTalks. So let's just jump right into this, shall we? Of course, technology works every time, so let me do this share screen, and we'll see how it goes here. And is that shown full screen? Okay, perfect. So look, let's talk about this idea of monitoring the nature and behavior of anthropogenic, human-made, human-derived objects in space. So the near-Earth space domain, things around the Earth in orbit, it's a complex system. Really, we have an environment that's very dynamic: gravity, solar flux, charged particles, these sorts of things. And when we have human-made objects, satellites, dead or alive in this environment, that interaction forces them to behave in certain ways. Not all are known, actually. So there's a lot of science to be done there. For operational objects, basically the space environment can create havoc in terms of the electronics, upsetting communications, and these sorts of things. And then in terms of their motion, so astrodynamics is the science that studies motion of objects in space. Certainly the space environment drives how these things are moving. The other part of this, which may be a surprise to you, is that because we have a number of participants joysticking satellites in this domain for a variety of reasons, we also have threats. And what that means is that human activity on the Earth is not just about benevolence and kumbayas. So that behavior also has translated on orbit into space. And so there are real threats on orbit that we need to be able to monitor. Near-Earth space is a finite resource. And what I mean is that although space could be considered to be infinite, but the region around the Earth is not. And we only put satellites onto specific orbital highways. And so what I'm showing you in this graph is taking the position and velocity of, say, 4,000 of these objects, computing their specific orbital angular momentum. So I'm just taking the cross product of the position into the velocity. I get h, specific orbital angular momentum. And you can see how these things look like little highways. Now, the color is based on the inclination of the orbital plane with respect to the Earth's equator. So 0 degrees inclination is something that's pretty much orbiting in the same plane as Earth's equator, and something that would have a 90-degree inclination would be a polar orbiting type of satellite. And so I didn't do any sort of clustering in this space, but you can already see how these things are separated in terms of the magnitude of their specific orbital angular momentum, so the energy in the orbit, and their inclination. And this is just to show you that we kind of have like these orbital zip codes where we put these satellites. And you can see that, clearly the dot size matters here, but these highways are becoming more and more congested because much of what we put on orbit doesn't come back. It stays there. Once it finishes its useful lifetime, when satellites die, for a great part, they just keep on going at these same speeds and staying there for very, very long times. So one of the things that we want to avoid, amongst other things, is harmful interference. We want to avoid the loss, disruption, or degradation of space services, activities, or capabilities, and even detrimental impacts to science. We're really interested in understanding the entire population of anthropogenic space objects. But one of the things that I tell my students is if you want to know something, you have to measure it. If you want to understand something, you have to predict it. Prediction is key. And we can't measure the entire population. That's unfortunate. So we can't actually perform a proper statistical census of the population. At best, we can only measure a sample of that population and hope that whatever conclusions we can draw from the sample are things that we can then extrapolate to our understanding of the remainder of the population that is unmeasurable, okay? But because we can't measure the entire population, whatever conclusions we do draw are mired in uncertainty. So one of the things that Rudolf Emil Kalman, the co-inventor of the Kalman filter, said, he said, uncertain data cannot provide exact models unless we apply prejudice to remove this inherent uncertainty. All right. So based on that, this is what I'm saying is the inferred anthropogenic space object population. Again, we can't measure the whole thing. So if we hypothesize what this population might look like going down to 1 millimeter in size, so a speck of paint all the way to the space station, we really think we have probably well over 1 million objects. But we can only measure things down to say about 10 centimeters, so the size of your cell phone, all the way to the space station. And if we look at that measurable, trackable population, we're really talking about 30,000 objects, of which about 4,000 are things that are actually working and everything else is garbage. So basically, we believe we are only measuring about 1% of the population of anthropogenic space objects. And of that 1%, there's probably 6% or so work and everything else is garbage. That's not so good. So I kind of turned our American model on its head a little bit and saying out of one, many. So out of one common environment, there are many competing needs. There are space safety needs. You want to avoid colliding with other people, because when collisions happen, satellites break and become many, many pieces of debris. From a security perspective, we want to make sure that we don't present ourselves as threatening to other folks, that we can somehow develop practices and protocols to allay these sorts of ideas that we might intentionally be trying to cause other people harm. And then from a sustainability perspective, really looking at near-Earth space as an ecosystem, looking at it in terms of a sort of pseudo-ecological sustainability, and how can we address environmental impact by developing sustainability metrics like a space traffic footprint as a carbon footprint analog and orbital carrying capacity. So to the point of orbital carrying capacity, we could think of these orbital zip codes, as it were, as potentially becoming saturated. And saturation of the orbital carrying capacity would look like our inability to prevent undesirable things from happening, right? It's like when our decisions and our actions can no longer prevent some level of undesirable outcomes. For all intents and purposes, we've lost capability to really utilize that orbit in a way that we intend to. Now, orbital carrying capacity in that sense is then consumed by both natural and anthropogenic space objects, and of the latter, both dead and alive. The idea of a space traffic footprint, such as a carbon footprint analog, would basically loosely be understood as the burden that any one of these objects places on the safety and sustainability of anything else. So as an example, I get my car, as soon as I turn it on, put it in reverse, I am now a burden to all pedestrians and other drivers. And even if they can see me with exactness, they know exactly where I am, and even if people can predict exactly what I'm going to do, the fact that they have to take my existence into account for their own safety is a burden. So that's how I'm trying to quantify this idea of a space traffic footprint. Now, something else to keep in mind when it comes to our knowledge about stuff in space is I'm going to kind of use this, Donald Rumsfeld, known knowns, known unknowns, that sort of thing, to basically say this. Think of the first term as what you are aware of, and the second term relating to what you have measured. And again, if you want to know something, you have to measure it. So a known known then is something that you are aware of having measured. That's good. A known unknown then is something that you are aware of that you have not measured. And so because of that, we have to ascribe some level of uncertainty to kind of account for the fact that we have not measured these things. The unknown unknown, basically enigmas, are things that we are neither aware of and we have not measured. So they're truly unknowable. And one of the things that we'd like to be able to do is try to see if we can aggregate massive quantities of disparate sources of information about stuff in space to see whether or not in this aggregated data set, have we unknowingly measured something of interest, right? We can pose interesting queries to this aggregated data set and see, is there something discoverable in the mutual information content of said aggregated data set? And so if the answer is yes, then we can go from the unknown known to then the known known, which is the place for ideal decision making. But this is how we sort of think about where our awareness and knowledge resides regarding stuff in space. So this idea of space situational awareness or space domain awareness, what is it? It's really just knowledge about what's happening in the domain so that it can facilitate decisions that lead to desired outcomes. So it has to really provide three things. This is how we measure my work regarding this stuff is anything that I'm doing making space more transparent? What is it? Who does it belong to? What can it do? Is anything that I'm doing work on making space more predictable? Do we understand where any given set of objects are going to be over the next few hours, days, months, maybe even years? And in any common scenario, maybe there's a predicted collision between two operators. Can we predict how they're going to behave, what decisions that they're going to make, and these sorts of things? So there's a cultural competency that needs to be brought into to bear on that. And I'm going to show you where that might be important here towards the end of these slides. We have a framework to somewhat understand the process that we have to go through in all of this. There's somebody, John Boyd from the 80s, kind of came up with this simplistic concept called the OODA Loop for observe, orient, decide, and act. And this is all to say that observations by themselves are insufficient to really meet our needs. We need to take the observations and translate these into a lingua franca, into a framework where we can make sense of these, know how to interpret them. And given that, then we can make good decisions and actions, hopefully, again, that maximize desired outcomes. Case in point, if all you're interested is in observations, this is kind of what you get. There are plenty of data lakes and libraries, and it's like saying, okay, well, the information that you want is somewhere in the room. It's there, just find it. Okay, how long is that going to take me to do, good luck if I have to make decisions in a time-sensitive kind of way. So we don't want just data lakes and data repositories. That's not good. What we want is we want curated information. This is the orient part of the OODA loop. Again, observations by themselves insufficient. We want to orient these things. Just like you go to a library, right? You know where to look for certain things. And so we want curated data, models as well, physics-based models, information at the speed of relevance, as some say, and expose those to a wide variety of inquiry, whether that be policy, scientific, or other. So what we've developed, this thing called Arcade, really is underpinned by a knowledge graph database called Astrograph, which we've developed here at the University of Texas at Austin. And Astrograph, the entire framework is a three-tiered kind of system. On the bottom floor, the ground floor, are sources of information that can be sensor data, it can be human-based information, semantic, and we don't require the data to be in any specific format. We want to say yes to all sources of information. And so what we do is we build interpreters that can then pull out the essential elements out of these sources of information and orient these, as in the OODA loop, translate these, map them into this mezzanine level, the middle layer, which is the knowledge graph database. And we use Neo4j as our graph database software for that. Now, this middle layer is now semantically labeled, meaning the nodes are entities and the edges or lines are relationships between these. And this really facilitates big data science analytics because it allows us to link disparate sources of information together. Again, back to the idea of trying to find these unknown knowns. What have we unknowingly measured by doing this? So that the upper layer, the top layer, the applications are really user inquiry and these sorts of things. So this is the three-tiered system. We've partnered with IBM here in Austin to have Arcade, and you can kind of see this three-tiered system again in this flow diagram way, where on the far left we have sources of information, the middleware, the mezzanine, leveraging IBM Cloud, and the graph database is Neo4j, it's specifically Astrograph. We have APIs so that machines can talk to each other. We don't require humans to be in the loop, and that facilitates large-scale computational capabilities regarding stuff in space. So monitoring the behavior of these objects. What are genuine threats in space? How do we infer intent? Because threats require the concurrent existence of three ingredients: opportunity, capability, and intent to cause harm. Opportunity and capability are things that physical sensors can give us insight into, but we don't have sensors that measure intent. No intentometers out there. So how do we do that? What is abnormal behavior? Surprisal, statistical surprisal is really basically the difference between what you observe and what your belief is or what you predict. If you know the truth exactly, that amounts to zero statistical surprisal. Your belief will remain unchanged in the presence of evidence. But if what you predict is pretty far off from what you actually observe, that is large statistical surprisal and affords you an opportunity to learn and refine your knowledge. We want to see, how do we minimize misconceptions, misinterpretations, right? We don't want escalatory behavior on orbit, people thinking something's a threat when really it isn't. How do we protect ourselves in the environment, incentivize behaviors that lead to increased space safety, security, and sustainability? How do we improve compliance? Can we use citizen science to do this sort of stuff? And so again, if you want to know something, you have to measure it. If you want to understand it, you have to predict it. In terms of the measurements then, on the far left, we have things that we can actually measure. So one question is, what combination of these measurables gives us insight into physical characteristics of these objects? Then what combination of these physical characteristics and properties gives us insight into functional and operational properties? And then moving to the right, can we develop a scientifically inferred taxonomy or classification scheme for the population, because that does not currently exist, surprisingly. Again, observations by themselves, insufficient. In fact, here's an example of detections versus tracking objects. So all the dots are things detected by this telescope called the Space Surveillance Telescope, a single night's worth of detections. The black dots are things that we have detected and believe we know the identity of. We have some catalog or database of objects and say, oh yeah, we believe this detection is object 123. Everything that's not a black dot is unknown. And this is what gets generated on a nightly basis. There are a lot of stuff up there in orbit that we have no clue what it is, where it's going, what it could possibly do. That's not so good. And the situation is actually getting worse. Another way to say it is that, look, I said that the trackable part of the population was about 30,000 objects ranging in size from cell phone to the space station. Most of those are dead objects, right? I said about 4,000 work, everything else is garbage. So for sure, none of the garbage is reporting its own identity, right? Because it's dead, it's garbage. And so one question is, or a challenge is, given detections of things that are not telling you what they are, how do you then solve that inverse problem of given data, what generated these observations, and can we solve that identity crisis of stuff in space? I see many people arguing about their algorithms, and they claim to know the truth about what's going on orbit, and that's utter and complete nonsense. So nobody has a data set that's so complete that gives us basically the truth about everything on orbit. At best, we can say that something is true. And so the importance of this massive data aggregation, big data, is to then try to get us closer to what is true. If you ask the US public truth for stuff in space, you might see a space traffic map that looks like this. But if you ask the Russians that question, you might see something like that. These things are not equivalent. They don't even overlap in many instances. Again, different people have different sets of eyes of stuff on orbit, and this is part of the importance of aggregating all these observations. Not only that, but even on a common object, if we ask 4 people, where do you think this object is located? You're going to get 4 different answers. And these could be statistically basically separated from each other. So right here, we're talking about maybe a few football fields between the dots, but a few football fields could be the difference between a real predicted collision and one that you shouldn't have to worry about. So we need to find the barycenter of these opinions. So one of the things that I say is, how do you know that you have the world's most accurate clock? And the answer is you have hundreds of them. Each atomic clock has an opinion of the time. You develop an ensemble of all these times being reported from around the globe, and you find the barycenter, and that center of mass of the time is what is the time for the world. Now, I said policy products as an example. Well, one of the things that we did was, at the behest of the United Nations Office of Outer Space Affairs, we decided to look at their space object registry because there's a treaty, a convention on space object registration. And so we decided to come up with a rating system. If people register their object with the UN within 120 days, they get 5 stars. If it's above that, but within the first year, 4 stars, so on and so forth. And we did a weighting scheme of this. The words in the treaty are register your object as soon as it's practicable. And the interesting thing that we see is that there are countries which on average take years to register their objects. Again, common treaty, it's a common international space law, but culturally widely interpreted. I mean, are the countries registering 5 years later, purposely trying to obfuscate things? Probably not. But as soon as it's practicable, apparently means different things to different people. And so you can't manage what you don't know. You don't know what you don't measure. And it's very critical that before we try to say we need more laws and more regulation, let's understand with data, with empiricism, how are current laws being interpreted and implemented, who's compliant, who isn't, so that we can then have discussions to, mitigate, any gaps as a consequence of these behaviors. So I am going to actually stop the presentation there, but I have some things to show as well with a new share here, which I will do. And this is just to give you, a picture's worth 1,000 words kind of thing. And so here I want to show you Astrograph kind of live. And this is what we're talking about. Basically, and we've developed this at UT Austin. And so what you're seeing is every single dot is an opinion about something in space currently orbiting the Earth. Here you see what looks like a line of pearls there. Those are mostly, Elon's, SpaceX has some satellites up there, the Starlinks, to provide global internet. So there you see a trail there. And if I zoom in a little bit, you can kind of see a little bit of the motion of these dots. Let's zoom in a little bit. Okay, here we go. Here's some that you kind of see kind of crisscrossing there a bit, perhaps. Here we go, right? So yeah, these things are up there. They're providing different services and capabilities, things that we care about in our pockets, right? Not just position navigation and timing, but also communications, weather warnings, climate monitoring, all that stuff. This gives you an idea of kind of the orbits that these things are in, roughly how far they are from the Earth's surface. And again, each dot is an opinion of some anthropogenic or human-made object currently in Earth orbit. And you can kind of get an idea of that. Another interesting thing to show, let's see if I have this right here. Yeah. Here we go. Conjunction streaming. So we have developed a conjunction streaming service that shows you amongst 19,825 objects, which ones do we predict are going to come within 10 kilometers of each other in the next 20 minutes continuously. So we have a continuous sliding window of 20 minutes. This gives you an idea of the busyness of the space traffic. These are things crisscrossing each other, just like you saw here earlier, predicted over the next 20 minutes. So this isn't things colliding, but it's things coming within 6 miles of each other. So the green dots are pairs of things where both are working. Yellow dots are pairs of things where one is working, one isn't. And red dots are things where both are dead. So you're left to hope that things don't collide. Most of these things are at this 900-kilometer altitude, sun synchronous orbit, and then relative speed spike at 15 kilometers per second. So that's 15 times the speed of a bullet. So the smallest thing that we're tracking here is like a cell phone. So if a bullet does damage at the speed of a bullet, imagine a cell phone going 15 times that hitting a satellite. Bad things happen. And it might be a satellite that you care about. So this is just to say, we need to do a better job monitoring what's going on in space. We need to incentivize sustainable behaviors in space so that we can utilize the orbit for a long term for future generations and all that stuff. And we're doing, leading research here at the University of Texas at Austin, where we've developed the first kind of crowdsourced space traffic monitoring system called Astrograph, which has already been serving people from across the globe. Thank you very much.
Thank you, Dr. Jha. That was very informative. It's so crazy. Like a cell phone can create so much damage in the atmosphere, and people don't even realize that. Well, we have a couple questions here that I wanted to pose to you that was from our audience. Our first question: if a predicted conjunction results in an intervention, say a laser shot to move one of the objects, then how will other interested parties be made aware of the change? Also, who decides who would conduct the intervention?
Right. So actually, the bad news is we don't have a way to do that. There's no way to reconcile or do this global coordination and planning kind of activity. There is a company called Slingshot, which has developed a product called Beacon to address this issue. And so Beacon is a platform where interested parties can communicate with each other and try to deconflict, try to come up with a decision on, who's going to move to avoid the playing chicken scenario.
Awesome. And our next question, is there any attempt being done to try to clean the junk that's in space?
Yes, there are a few companies like Astroscale out of Japan that are developing a space garbage cleaning business. The European Space Agency in 2025 is going to demonstrate the technology to do that by going and grabbing, the mission is called Clear Space, out of the École Polytechnique Fédérale de Lausanne, the EPFL in Switzerland. And they're going to go and grab this Vespa payload adapter and demonstrate that in 2025. So there are a number of people trying to look at that as a business. Nobody's really paying top dollar to do that yet. Part of that is because we need sustainability metrics in place so that you can show what is the impact, financial, environmental, of removing any given object. And I think when you do that, then you can monetize the cleaning business. But until then, probably doesn't make too much sense. And the biggest culprit on the spread of debris, so if we consider the proliferation of debris, kind of like COVID, we want to flatten the curve on that. Right now, the biggest reason why we're not flattening the curve on the spread of debris is non-compliance with what the science has said. Surprise, surprise, right? Just like people aren't masking and doing the vaccines and stuff, people are not complying with what scientists have said. Hey, do these things, you'll flatten the curve on the proliferation of debris. People are just non-compliant. And then if people could be more compliant, then there's room for removing stuff. But the bad news is, microplastics in the oceans will never disappear. So the ocean will never be as pristine as it once was. Same could be said about near-Earth space.
Interesting. And so another question, just curious if you are also monitoring the Lagrange points, and are they getting crowded too?
Yeah, so I personally am not monitoring the Lagrange points, but there are people that have large pieces of glass telescopes looking at these things. And, it does make sense for some debris to find its way there if things got pushed at the right time in the right direction, sort of thing, because of a couple of them are stable. There are several that are unstable points, but at least the stable ones, you could think that you might find some more debris in these regions.
Okay. And another question, as we insert more objects into the cislunar space, how do you propose that objects will be tracked, especially those closer to the moon or orbiting around the strategic Lagrange points in the Earth-Moon system? Will this be a non-Earth-based radar solution or something else?
Yeah, so I think that, we really need to be pushing for autonomous space systems, because that's really the only way to close the loop on this, in my opinion. So it can't just be things, eyes from the ground. We need eyes on orbit. We need in situ eyes on orbit, things that are actually probably orbiting the moon and going back and forth between the Earth and the moon, transiting between the Earth and the moon. So we need a system that combines ground and space-based capabilities. And again, looking towards autonomy. I have a name for this. I call it AMAD, which is the autonomous hive mind for advanced decisions. And I love the hive mind kind of thing. So a collectively intelligent system. That's what we need.
Awesome. And another question, you kind of touched on this already. What's the approximate mass of dead objects in space?
There's this guy, Darren McKnight. He works now for Leo Labs. He has a better thumb on this, but look, it's many, many metric tons of dead mass on orbit. So it's bad news.
And do we have any idea what those are? Or
yeah. I mean, look, it's like the big ones are rocket bodies, dead rocket bodies. People were concerned about, this rocket body from China, this Long March 5B earlier this year that kind of re-entered, and people were like, oh, where's this thing going to land? That sort of stuff. There's another 1,000 of those in orbit, going back all the way to like the 60s and 70s. And A lot of these aren't going to re-enter because they're sufficiently high, but they're ticking time bombs in space. And the thing is, once they explode, they become many, many tens of thousands, hundreds of thousands of objects. And if something collides against them, then the same thing. And these are pretty much owned by, just 3 countries: the U.S., Russia, and China. So.
And we have 2 more questions. What is the Eyes on the Sky prototype?
Yeah. So thank you for that. So one of the things that I realized early on is that me doing these talks, it's great to speak to everybody here, but I'm not really reaching enough people. And when I gave my TED talk in 2019, when I became a TED fellow, I realized that a 5-minute talk talking to non-space people got me 2 million views versus talking in the echo chamber of the space community. I don't need to talk to space people. I need to talk to the rest of humanity. And so Eyes on the Sky is really a project. Part of it is an immersive experience, a mixed reality experience. Can we basically create this mixed reality experience where maybe a dozen people at a time actually go to this location where not only is it kind of this augmented reality, but there are objects in this in the sky dome kind of experience where the users have some agency. What happens is in part dictated by what you're doing with objects. So really a mix between physical and digital experiences. So that's great. And I'm working with, College of Fine Arts, Sven Ortel out there, and Aaron Riley here at UT to do that. But concurrently, we're also looking at the possibility of developing a documentary series on space sustainability that really looks at how certain indigenous people have never abandoned this idea of being stewards and custodians of their environment, and the principles of this traditional ecological knowledge and how we can use that to better inform how we can achieve sustainability in what we do in space. And so that's more of me kind of being like a Tony Bourdain, but for space, and basically going and interviewing people and just having very real, human, candid conversations about this, but really founded in the idea that everything is interconnected and that action is best when born from a place of love and compassion, and looking at this intergenerational contract of stewards versus owners of stuff.
Awesome. That sounds like a great project. And for all the viewers online, we've posted a link so you can find more information about that project that Dr. Moriba Jah is working on. So thank you so much. We really appreciate your time and your dedication to this effort. And so we're going to wrap up from here.
Excellent. Thank you so much. Honor and a pleasure.
Once again, thank you, everyone. Thank you all for joining today's webinar. We hope the conversation was valuable. If you would like to learn more about future webinars or to hear more about hot topics that are changing the industry, please be sure to follow us on our social media channels. Next, we want to highlight a few of our professional development short courses and future webinars. As you've heard today, lifelong learning and technical adaptability is fundamental in preparing individuals to remain competitive in today's workforce. To support the needs of professional engineers, Texas Engineering Executive Education will be providing an engineering exam refresher course. This course is meant to assist engineering students near graduation and working professionals in preparing for the fundamentals of engineering exam. Successfully passing this exam is the first step an engineer must take on the path to registering as a professional engineer in the future. Review the course dates below and sign up today. Next, we want to thank the 3 units of the Cockrell School of Engineering that helped put this wonderful program together. First is the Texas Engineering Executive Education, who works to reskill and upskill companies' current workforce, either through our master's degree programs, graduate certificates, or short courses. So if you have a need around STEM education or training, make sure to contact our department to learn more. Next is our PTEX department, or Petroleum Extension of Texas. This department has been around for over 75 years, serving the oil and gas professionals with skills training, either through e-learning, publications, online, or in-person training. We have the training to meet your energy-related needs. And last but not least is our research relations team. This team partners with industry to solve some of the world's biggest problems in energy, water, transportation, space exploration, and many more. The Office of Research Relations works to facilitate and derive high value from research collaborations between companies and UT's researchers. So if your company would like to partner with Dr. Moriba or other professionals to explore additional research opportunities, please email the Research Relations Office to initiate a discovery discussion. All 3 units are here to serve you and your company through education, training, and research. So feel free to contact us at any time, and we would love to collaborate on helping you reach your company's full potential. And as we continue in the TexTalks series, I want to make sure you're aware of our upcoming webinar. On October 15th, Dr. Irhan Kutunoglu will be discussing disaster decision-making, and he will be answering the question on how come we still have devastating weather-related tragedies despite increasingly powerful weather prediction tools. Could it be as simple as connecting the dots? Make sure you tune in to find out.